Okay, again, welcome to my talk about machines that learn by playing. It was in 1956 that a group of scientists came together to found what we now know as the field of artificial intelligence. And they had a quite cool conjecture, namely that every aspect of learning or intelligence can in principle be so precisely described that a machine can be made to simulate it. So there was a lot of research going on, but only 50 years later, or more than 50 years later, a company was founded, namely DeepMind, with a mission to solve intelligence, to crack this problem. And why then? The observation was that machine learning, in particular deep neural networks, proved to be increasingly powerful at that time. And the key focus of our work is to learn to self-improve from own experience, because we think this is one of the key properties an artificial intelligence system should have. So in this talk, I want to take you in 5 steps in the development of a capable self-improving agent and take you to that journey so that you can judge how far we've gotten on this exciting question. Before we start, I want to just give you a rough idea, because it's always a question how learning can be done in a computer or in an algorithm. And the way we do it is by neural networks, which are just a simple mathematical model of the brain, and they can be algorithmically fit to data. So basically, the only thing that you need to know is that neural networks map numbers at their input to a certain number at their output. And the trick is that they have a lot of parameters, and by changing these parameters or weights of the network, we can change this mapping. So basically, we can learn arbitrary reactions to some inputs by changing these parameters, and we know how to do this. And this is called learning, and this is a basic toolbox of everything that we're doing and everything that is coming next in my talk. And recently, we understood how to train huge neural networks. So previously, they were rather small, but now they are getting really big, having several layers. And so the knowledge that we can learn and recover gets more and more complex. And this makes them very attractive for cracking the problem of artificial intelligence. So step 1 is how to understand how to learn from success and failure. So the observation is that learning from own experience by making successes or experiencing failures is a central feature of human intelligence or general intelligence. An example is learning to ride a bicycle. Nobody can exactly tell how to use your muscles, how to balance exactly. That is something that everyone has to learn by themselves. And just by the observation of, oh, I'm successful, I can ride a couple of meters, or I was not successful, I fell over, you change something, your parameters, and then after some trials, you get better and better at it. And even if you cannot describe what exactly you're doing, you can ride a bicycle. And this is what we want to bring to machines. There's some very early work by Rich Sutton, who basically founded this whole area of reinforcement learning for algorithmic treatment. But how can we make an artificial agent? We want to bring this in a computer program. How can we make it to learn from success or failure? I don't want to go into the details, but I want to give you at least the gist of what we are actually doing and what our current work or what our daily work looks like. So the central idea is that if we want to learn from success or failure, we typically have a sequence of decisions that we have to take in order to be successful. So for every decision that we take along the path, we get a reward. And this reward can be imagined as just being a positive number if the task is solved. And then learning can be expressed as simple as collect as much reward as possible, collect as much of these positive numbers as long as you can. Mathematically, this can be described as maximizing the sum of rewards that occur if you apply a certain policy, and you want to find the best policy that maximizes this reward. And so out of a sudden, learning becomes a mathematical optimization problem that we know how to solve. And what we are doing is basically to put these algorithmic methods, these mathematical methods, back in our learning algorithms, back in our learning agents to solve these kind of problems. The neural networks come into play because we want one crucial aspect of this solution method is that we solve the problem of computing the influence of each decision on the final outcome. And their neural networks are really good to represent this mapping. And as I told you before, we can learn them and we can adapt them as we grow our experience. So in this context, riding a bicycle would become very simple. There's a reward of 1 if we are moving on the bicycle and 0 if we are falling. So a successful policy that collects as much reward as possible would collect a lot of 1s and would end when we are falling. So a better policy would just increase the number of time steps that we're actually riding the bike. And this policy can be called to solve the task. The agent architecture looks like this. So basically there's an actor that has a certain policy pi that interacts with the world, with an environment, observes the next state, and according to the state, applies the next action. All of these state action pairs are given to a learner that then produces this mathematical optimization and comes up with a slightly improved policy. And so by iterating this process over and over, we're finally getting to solve the process. But only the outcome has to be told to the learner and not how to do this. And neural networks represent the value function and the policy in this case. So the first, or one of the first big successes of DeepMind was to apply this to a game called Go, an Asian board game. Board games like chess and Go are challenges for human intelligence. And chess, as you probably might know, was solved in 1997 or 1996, where for the first time a computer system called Deep Blue beat the human world champion in chess. This was basically built on putting a lot of rules into the game. Go has a much bigger complexity, so it was a long-standing challenge for AI. In 2016, a group of colleagues at DeepMind, around David Silver, tackled this challenge. And actually, by a combination of learning by examples of previous expert play and self-improvement, we were able to beat the world champion Lee Sedol in Go, which was a big breakthrough for AI. But we didn't stop at that. We developed another system that completely learned from scratch. So no expert data was used to train the system. This started completely with a completely random network and got a reward of 1 if it wins and -1 if it loses the game. And then millions of games in self-play with this clever algorithm have been played. And at the end, an incredibly powerful play emerged. So in the AlphaGo example, after 8 hours of learning, the system learned to beat the previous AlphaGo system that beat the world champion considerably. So was on par with the system that beat Lee Sedol. And after further learning, it became what is now known as the best Go player in the world. And for a simple, so-called simple game like chess, it only took the system 4 hours to completely learn from scratch how to play chess on a world champion level. And again, here the machines are the best chess players already. So Stockfish is the best, and after 40 hours it can be beaten by our system. And if we give it more training time, then it beats it even more drastically. So then we enter step number 2. Now we can learn in principle, but as I told you, we played millions of games to get to this level, which is probably acceptable because we can do this in simulation. But if you want to do something in the real world, then training for millions of trials is probably too long. Probably if you imagine a robot training by this, then the robot is broken before it ever learns something reasonable. So the key idea now was to store experience explicitly. So this was the previous learning architecture, and now we extend this by adding additional memory. So we can replay this experience that we have collected over and over again. Basically something like dreaming in humans. And this also came with a new algorithm called neural fitted queue that a colleague of mine and I proposed independently in 2005. And it also came with a new learning algorithm, and which I also printed so that you have a rough idea how these agents look internally. And it's basically not surprising that all these things that we discussed before, namely to do something with the experience, to have a reward, and to use neural networks in order to store this knowledge, occur somewhere at some stage, at some parts in this algorithm. But what can we do now with this novel learning? And this I want to show you on a physical example. So balancing a pole on a card is a typical control problem that is learned by control students in one of their first semesters. But in order to do so, they have to know a lot about physics. Our agent does know nothing about physics. It only gets the what to do, namely to balance the pole by moving the card back and forth. As before, the reward definition, the goal definition is pretty simple. If the pole is upright, then we give a reward of 1. And in all other situations, we give a reward of 0. So if we would apply the basic reinforcement learning approach, the previous approach to that, we needed more than 1 million trials in order to actually learn that problem, which is probably okay if you consider that the agent at the beginning has no idea of how physics work. With a new algorithm, NFQ, and having this memory of the experience within the loop, we could reduce this number to less than 300 trials. And this out of a sudden makes it from a nice to have technique to something that could really be applied to real world systems. Oh, can you play the video, please? Okay. So now you see at the beginning, the agent has no idea. So it moves the car somewhere, gets close to the border. The trial is ended because it should stay within a certain area. And in the background, you see how the neural network is adapted. You see the iteration that NFQ is doing. So something is happening that is not so clear to see, but you see that the policy slightly changes of the agent that moves the car. After about 25 trials, it has at least learned to avoid the boundaries. So it stays alive for the whole control time that we give to it, which is already a success, so it doesn't fail immediately. And after 29 trials, it also has learned to somehow stay away from the boundary. And now also you see that the pole slowly starts to get more energy. After about 80 trials, for the first time, it actually achieves to get the pole up. But of course, this is only part of the truth because we want to balance it. And for this, which is actually much more difficult, it took another 100 trials of that. But now it kind of achieves to balance the pole and also keeps the card kind of in the middle of the track. After another 50 trials, it now carefully swings up the pole and actually achieves to stay much better in the middle. So all the control behavior is much more calm. And finally, after 240 trials, it learns how to swing it up very quickly and then is able to balance the pole basically forever. And this is without having any knowledge about the physics. It just can apply any voltages to the card. It just gets the reward of a 1 if the pole is upright and the card is in the middle of the track, and 0 otherwise. So all the control knowledge is basically learned by the system in itself in a very short amount of time. Stop the video, please. Okay, now we can learn in principle, but can we also go a step further? So can we do something like mastering an environment or learn even more complex tasks? And to do so, we took another look at how humans learn. The key idea is basically like babies, play, collect experience. Then if these experiences are successful, learn the simple skills, then continue to play, using now these simple skills to collect even more interesting experience. So the agent can use a set of interesting rewards instead of only one. So again, this was the previous picture where we have a memory. And now instead of training only one policy, we train a whole set of skills or a whole set of policies, because now we have a whole set of things that are rewarded by the agent. And with this, applying this set of policies, we get better and better. So this is basically the idea of the scattered auxiliary control algorithms, that we replace the single reward by a set of interesting rewards. And for every reward now, we learn a separate policy that then can be used to explore the environment even more. And since we now also have a set of policies instead of only one, we need someone who decides which policy to apply. What do I want to play next? And this is called the scheduler. And the interesting thing about the scheduler is that the scheduler itself learns to do something. Namely, the scheduler has an interest to learn to schedule the skills so that even more interesting behavior is observed. One task that I want to show you next is to clean up bricks into a box. So the final task is of course difficult to achieve by random playing, because you have to lift the lid of the box, you have to take the bricks, you have to put them in the box and close the lid again. But what if we give it a couple of rewards? Namely, tell the system that it's good if you touch something, if you move the bricks, if you open and close the fingers, if you lift the brick, if you arrange the bricks. So basically to get more and more control over your environment. By this, the agent plays and acquires more and more complex skills. Okay, unfortunately, this should be an animated GIF, so the robot that you see now should be moving. So this is only a picture here, but I can describe it. So what you see or what you should see in the untrained phase, the arm just moves around without doing nothing, but occasionally he touches the bricks. And since it gets rewarded by this, for this, it deliberately learns to touch the bricks. So now, by these occasional touching the bricks and being rewarded for that, it actually learns a skill that deliberately goes for the brick and touches it. And by touching it, it at sometimes also just occasionally grasps it and lifts it. And since also lifting the bricks is rewarded, it has now a policy that is able to lift the bricks and put them somewhere. So by then being able to grasp objects and put them somewhere, the agent is also enabled to put the objects left and right of each other, so to give them a certain order. So it gets more and more capabilities in order to play around with those. And finally, it also learns to stack these objects. And now he has a lot of capabilities how to manipulate these bricks, and occasionally also opens the box. So finally, at the end, it is also able to put these bricks into the box. And again, I apologize that this GIF is not playing. Otherwise, you would see how the agent actually can fulfill this task now perfectly. The diagram on the left shows also something interesting. The blue line is something if you would only execute these skills in a random order. So the scheduler would just be arbitrary and sometimes does reaching a skill, sometimes it does touching a brick, sometimes it does opening the box. And the red curve shows a scheduler that has learned to execute these skills in a deliberate order, namely so to increase the experience that it actually observes. And when we apply this learning scheduler, then the overall learning of the task goes much faster than if we only would apply the execution of the skill randomly. And again, one important aspect of this approach is that it is not tailored to a certain architecture or a certain robot, but it can also, if we exchange, for example, the robot arm with a different topology and have fingers instead of the normal grippers, then exactly the same agent with exactly the same reward would be able to solve the task completely with a different policy, because now the capabilities of the robot are different, but the learning itself, the learning setup would be exactly the same. And this would also go if you go for other tasks, like, for example, stacking Lego bricks. So now we have an agent that is capable to learn a lot of tasks and also to learn them data efficiently, because it reuses the experience to learn a huge variety of different skills. But in the last examples, the rewards were still kind of tailored to the domain. So we said, for example, grasp the brick, or order the bricks, or open the box. The question is, can we kind of come up with more general rewards that work in any learning scenario? And there we had the simple idea to make something interesting in the world, namely to try to change the values of the incoming sensors deliberately. And by doing so, we hope that the agent itself discovers interesting skills without being told to explicitly do so. So the general rewards are changing sensor statistics, and you see this in the animation to the right. So we have a camera that observes the scene, and then we can filter the camera for different colors, and we can make a color diagram where the majority of green pixels, for example, is. And then a simple reward would be move the majority of green pixels to the left, to the right, or up and down. And this can be done for any colors. And this simple reward and very general reward leads to that the agent gets curious about manipulating its environment in a curious way. And with this approach, we were able to learn on the real robot to grasp a huge variety of objects, just because it was curious to move something in its environment, and moving the objects to the left and to the right, moving the objects up and down, or the colors up and down, leads the agent to the intention, because the only way to do this is basically to kind of interact with the robot. And by this simple trick, it learned how to grasp and lift it. And on the right side, you see an even more surprising experience. It could learn the ball in the cup, where it only observes the scene with cameras and is rewarded if the ball is in the cup. And the rest is just learned because it is curious at the beginning to swing the ball, because then something happens in its sensor space. And at the end, it discovers by this that bringing the ball in the cup is the final intention by the user. So even very complicated tasks can be learned by this technique. And this can be also brought to other domains. So for example, here we have a couple of locomotion creatures, one with 6 legs. And at the beginning, we tell it, just do something with your internal sensors, like moving your right leg or your front leg. And for different creatures, it comes up with completely different policies in order to do so. So for example, if you only have 2 legs, it's not about only lifting one foot, but you also have to balance somehow. And sometimes it also finds very creative solutions. So for example, if the robot also has arms, then the best way to lift the leg is actually to lie down, because then the foot can be lifted much higher than just by lifting it and trying to balance. And with the same thing, you can also make the creatures move by just say, change my internal sensor, like an IMU, for example, to do something interesting. And again, here, the rewards and the agent architecture, the learning architecture is the same for all creatures, but the results are really different. So we could even learn to move when we have only 3 legs. We can learn to walk on 2 legs. And even if we gave the robot skates, it learned how to move forward by a completely different movement, but it still achieves to change the IMU. So this is one step forwards in order to be much more general with our learning architecture and putting much fewer prior knowledge about the domain into the learning agent. And as I said, data efficiency is one of the key properties of our agents, because we want to apply it in the real world. And this is an agent that learned to walk on a real device with less than 5 hours of training. So balancing first on the left foot, on the right foot, and then learning to move forward. Okay, and with that we are at the final step, step number 5. How can we take this even one step further, namely not only to show some behavior, but actually somehow bring experience to knowledge? And this is some recent work that we did, which we call the collect and infer framework, which has the idea that an agent always collects experience in form of data streams and has to transform this into new forms of knowledge, where knowledge now is not only a policy, but can also be something, a prediction what happens next, or a predictions what could be good rewards, or predictions about statistics, with the idea to collect even new experiments and to learn even more. So the architecture that we have now, which saves all the data, learns a couple of policy, changes to something that has a couple of learners that always work in the background on this huge memory of experience and come up with different ways of representing knowledge, like policies, models, representations, rewards. And I just want to give you, because this is very recent work, I just want to give you a simple example where this could go for. We made our agent learn to come up with its own rewards. So it now rewards itself, or it puts basically its own goals forward. And the motivation for that is always to be curious. And when we apply this to a biped, as you see in the video, it first learned to walk and to stand and using the arms to go further. Then it started to learn to balance on a single foot. It learned to safely sit down and not break itself. It jumped backwards and catched itself. And it also learned to do some gymnastics after some time. And for us, this is kind of a way going forward. So to reduce more and more even the way that we tell the robot what exactly to do, but just giving the idea of being curious and explore what it can do with its body. Okay, so where do we stand with respect to artificial intelligence? I think we have made a big progress on self-learning agents with respect to task complexity. So we are now able to even deal with very large action spaces, with continuous actions, with very large state spaces, even on real robots. We have increased the data efficiency considerably. So now we're even, as I showed you in the video, in some of the videos, we're even able to learn directly in the real world. And by reducing the amount of prior knowledge, for example, the exact specification of what reward to fulfill, we also increase the autonomy of these learning agents. So it's already a great engineering tool to learn feedback controllers instead of manual design. So there is a potential for broad industrial applications of this technique already, because here we specify the what instead of engineering the how, and for complex plants, this can be a really big advantage. The question is, did we kind of come closer to the original idea of solving intelligence? The answer is maybe. So there's a recent article by David Silver and other colleagues at DeepMind who claims that reward is enough. This thesis has to first be proven, but we in our team, we believe that enhancing this method and improving this method forward will at least allow us a potential answer to what are certain ingredients to build an artificial intelligence. And with that, I thank you for your attention, and I'm looking forward to your comments, remarks, and questions. Thank you. And I want to thank my team at DeepMind and at my previous universities.